Hello, and welcome back to Vegas October 1 Sounds. Tonight we're going to be very, very simple and very, very powerful. I'm going to, in the next 30 minutes, give you, the listener, the power to discern and argue that there is simply one shooter at the Las Vegas shooting. And it's really quite a simple argument if you understand it. And the argument goes like this. Let's presume for a moment that we have a point at which we are recording sounds. Oops, whoa, a little big there. That's okay. Just as was happening that evening with Vegas, somebody's got a audio recording device of some kind right here. And let's say further that we record some sounds there. And the nature of that sound looks like this. We've got a pulse there and a pulse there. In fact, we've got 5 pulses, all separated by 1/10 of a second. Okay, so 1/10 of a second between pulses for a grand total of 1/10 of a second for a grand total of the total duration from peak to peak then is 1, 2, 3, 4/10 of a second. So 4/10 of a second long. Now we can arbitrarily define at what time we receive this pulse, and let's just say that we receive it at I don't know, let's just make it easy. Let's say that we receive it at time 1 second. So our global time now, this pulse is received at 1 second. Now, the question becomes, how is this pulse, this sound generated? Well, if you want to assume 2 or more shooters, then you have to come up with a scenario. Let's put in 2 shooters here, and I want to make it easy. I'm going to put them in equilateral triangle situation. So to do so, I will put in something here. Let's say a source of sound there and a source of sound there. And to make it easy, let's say that the distance between them is 1,000 feet. They're all 1,000 feet apart. And let's further assume that the speed of sound that night is 1,000 feet per second. So under that scenario then, the time it takes sound to travel from any point to the other point is about 1 second. Okay, so by simple arrangement, let's say the following happened. We had 2 shooters. Okay, and shooter A over here emits some pulses, and he emits a pulse there, and then he skips some time and emits another pulse. And shooter B, and these don't have to be shooters, it can be any sound sources. This works for any sound source, which is a point source, and the sound propagates in a spherical propagation. He emits 3 little pulses. Now for those to combine and produce the result down there, then since this is 1 second propagation time from B to, in this case the receiver's at C, and we want those 3 pulses to align, this one would have to start at whatever the time is there, 1 second plus 1. So that'd have to be at 1.1 seconds. Okay, and this one would have to be, let's go to a different color in here. This one would have to be at, we've already marked it, 1 second. That's great. Alright, so for that to happen, for this first pulse here to arrive at the time 1 second, and since there's a 1 second propagation delay time here, this would have to occur at 0. Time 0. Alright, and for this one to arrive at 1.1, it would have to happen at time 0.1. and so on and so forth. A tenth of a second there, a tenth of a second there, and the gap enough in there to assure that this one arrived at, let's see, 1.1, 1.2, 1.3, 1.4, 1.5. So this one would be 0.5. And these would be 0.2. It doesn't quite add up, does it? 0.2, 0.3. So this is 1, 1.1, 1.2, 1.3, 1.4. I miscounted. Always good to count, right? So let's put it back, 0.4. So, shooter A fires 2 shots separated by 0.4 seconds, and fire B fires 3 shots separated by 0.1 seconds each, but starting at time 0.1, and this guy starts at 0.2. They both propagate 1 second each, so this is 1,000 foot here. All of these are 1,000 foot, and I'll mark it by 1K. So the propagation delay time is 1 second, and they both propagate down, and we record this little pulse here, all of which is nice and even 0.1 seconds apart. Now that's a contrived situation, I agree, but but I'm going to bring up the real thrust of the argument. We have one recording this. Let's bring in a second recording device, and that recording device is going to be over here, and I'm going to separate it from point A by, you guessed it, 1,000 feet. Therefore, the propagation time between A and, we'll now call this D, is 1 second. So the question becomes then, what is recorded at point D? Now hang in here with me, because we're just about done with this first part of the argument. Okay, well, let's take this one up here first. So at point A we got something at 0 and 0.4. It propagates along this path to D, which is 1 second. So we've got a mark there at 1, and then we've got another mark at 0.4. Excuse me, 1.4. Alright. Now, for this one up here at B, it has to propagate from B to A and then A to D, a total of 2 seconds. So, we let's define this. Here's 2 seconds there, roughly speaking. So at time 2.1 we get our first pulse, and then we get the second one and the third one. So 2.1, 2.2, 2.3. Presuming I've done all the math correctly. So now, what does that tell us? That says that by having 2 separate recordings, if the patterns of sounds received don't align the same, then we have more than one shooter. Conversely, if instead we had received here, if D had received this pattern, the 5 pulses starting at 1 second, then we would have had one shooter. Now that's a simple enough argument. I think that the math is simple enough that anybody can understand it. And this can be generalized into 2, 3, 4, 40 shooters, but it gets kind of complicated. But the point is that if you have one shooter, one source of sound, and it's a monopole, as we call it, or a point source, and it propagates away from that point source at the speed of sound, that no matter where you put your recording device, you will record the same exact sequence of pulses. Now, they'll be delayed by, the lead-in time will be, if this were 2,000 feet away, then there'd be a 2-second delay, and then the pulses would start. But it would always be 5 pulses separated by a tenth of a second each, as opposed to this up here, which clearly demonstrate that there's more than one shooter. Now ask yourself this question. What does occur in Las Vegas? Well, let's go look. Let's go look at what Las Vegas looks like. So, copy this down, mull it over, It's a very simple example, and it'll forever be beholding. I don't know what you can call this, but just call it sound in motion, or sound not in motion, or multiple shooters versus one shooter, whatever you want to call it. It's simple enough that almost anybody should be able to comprehend what's going on this. I said almost everybody. If you have a real strong belief that multiple shooters were involved, then this argument probably won't even reach past your fingertips. You may not even be watching this video. But for those who are dedicated to this channel, or who want to know what it's really about, this is about the simplest way I can demonstrate to you that there was only one source for the those volleys that were fired on the October that evening. So let's go look at some I just happen to be working on something that might be relevant. Let's see, I've been working on volley 7. So here in this diagram, I have 4 different locations. We have the Raymond Page, which is up there near exit 2. We have the Hartman, which is on top of the Mandalay Bay. We have Corey Langdon video, and then we have a video that's recorded down very close to the front of the stage middle. And this is for volley 6. And you'll notice here that with some exceptions, with some variations, and I'll explain those momentarily, that this isn't volley 7, this is volley 6B. Do I have one for volley 7? Well, it doesn't really matter. But you'll notice that these are pretty darn similar. And if I were to bring down Ray and, well, let's see, which ones are the closest? I would say Ray and Under are the closest. So if I were to overlap Ray and Under, you'd get a pretty clear indication of how close they are. In fact, here's something for volley 7, where I have plotted. Now that's shot count, though. That's kind of a little bit more complicated. I want RPM. Here's RPM. And that's far too many, but let's look at this one. Well, that's enough. Okay. Again, that's shot count. And let's see if we can work with this one. Here I plotted volley 7 on a scale of shots, and the up and down amplitude is the size of the time between shots, and any variation must be accounted for. Now in this case we have 1, 2, 3, 4, 5, 6 videos, and you notice they agree pretty well. And the variations, say like with the green one, which is Hartman, are probably due to the fact that Hartman isn't line of sight, has to refract around the corner. But for the others, let's see, purple has a little variation there. Taxi, the taxi was moving, and you'd expect that. This is green and purple, but the other ones are all pretty consistent. I guess the first picture was the best, even though it's not volley 7. Here you see the same pattern, as we discussed, the same pattern for 4 different locations throughout the venue, separated by hundreds, if not a couple thousand, not 1,000, but 1,500 feet in a couple cases. Oasis is, I don't have Oasis in this one. Oh well. So anyway, and this occurs for every volley. These are the muzzle blasts. Muzzle blasts are modeled and conceptualized as monopole sources radiating equally in all directions, although for the Mandalay Bay they aren't. They come out the window and then they form half of a monopole. But nevertheless, you see this exact same pattern for all the videos that are semi-static. Now for those videos where the people are running, then the distances change, because for every foot that you move, you gain about a millisecond of change in this. And that's what was happening in the dark blue ones here, is that these are not aligned properly with the light blue because the taxi was driving around. But once she got her act together and came back to the spot she was originally in, they aligned perfectly. So, this is the argument. If you want to argue that there's multiple shooters, then these patterns have to be different. If you want to argue one shooter, then these patterns have to be the same. And in all my measurements for at least 100 videos, I have this type of alignment. That is, when you subtract out the initial delay to the recording device for each of the volleys, and then line them up, lay them out side by side, then they match if you account for any motion that might occur in the recording of the video. So that means that 1, you generally have a relatively static recording location. 2, you have a relatively static source of sound. And that 3, there's only one sound source. There's not multiple sound sources. And I don't care how you roll it. All you have to do is line up, a few of these patterns, and then the rest of the volley is secure. Now this technique, the same exact technique, works for the entire sequence of volleys. If I take the entire sequence of volleys, or at least, let's say I take 5 volleys from one video, the same 5 volleys from another video, I plot them out like this on this huge graph, and if they all line up, guess what? Then all the volleys came from the same source. And it's a very simple concept. If you had 2 shooters, you'd have each recording location recording a different pattern of events. And there's no simpler way of putting it. Now this doesn't work for sonic cracks because supersonic cracks don't follow the same physics, and they're all over the place. No matter where you go, you have a different pattern of supersonic cracks. A lot different. And you can go read some of my other videos and all that, but this is the simplest way to put to rest the argument that there are multiple sources of sound. And I don't care whatever you want to believe, whether it's amplified recording device, etc., etc. There's only one source of sound. Period. For the muzzle blasts, anyway. These are all related to muzzle blasts. All right. Well, I hope you have enjoyed this little trip into simple physics, simple understanding, and powerful statements regarding what happened on October 1 of 2017. Thank you for your time, and we'll grab you in the next one.